Hello, everyone. Welcome to another live stream. We are going to try an experiment today. I have said we'll do a Q&A for scientists. I've been doing lots of live streams, different series that are intended for anyone. I thought it would be interesting to try and do a live stream that's intended to answer slightly more technical, slightly more scientifically informed kinds of questions. I make a big effort to try and give answers that I hope anyone can understand. I think what I was going to try and do here is to give answers that are more the kinds of answers that I would give if I was giving a talk to technical folk who have kind of studied physics and math and computation and things like this. So that's what I'm going to try and do here. This is just an experiment for today. We'll see how it goes. So I have a number of questions saved up here that have come in that seem appropriate for this. Let's start with one from Hassan. It says, I'm intrigued by the idea of computational irreducibility in biological evolution. Can you elaborate on how this concept challenges our understanding of complex systems? Now, by the way, another thing I'm going to do here is sort of change my rules and not just talk, but also show some pictures. So let's start off talking about, well, the concept of computational irreducibility and the sort of challenge of biological evolution. One of the features of biological evolution is this question of how does it come to be that life produces all these complicated forms? One might think that even if one was doing natural selection, trying to select for organisms that would have high fitness, that will produce many offspring and so on, that there would somehow be a kind of simple mechanical, this is the best solution answer. But yet, one of the things that seems to happen in biological evolution is that we get all these incredibly complicated forms. We get all these biological organisms that seem to have sort of lots of complexity to them. And the question is sort of, why does that happen? And is that because the world's a complicated place, and in order to succeed in being the fittest organism in your environment, you end up having to have all these complicated extra pieces, or is that a feature of the process of evolution? So I've been looking at these very simple models for biological evolutions just starting a couple of months ago, and I just posted something about this very recently, a week or so ago. And let me explain how these work. So here's an example, and kind of the idea is that this is showing sort of a very idealized organism with a very tiny genome, and then it has the actual development of the organism. So the notion is, here's kind of a genome that says this is how you build the organism. And this is a cellular automaton system where the thing is set up as a line of cells. Each cell in this case can be either white, red, or purple. And we're starting off from just one red cell, and then we're following these genomic rules to build this pattern. And in this particular case, the pattern lives for, I don't know what it is, 90 steps or something, and then dies out. And so then the idea is, well, what could something like biological evolution do operating on a system like this? Well, biological evolution, let's see how I do this. Biological evolution operates on genomes. It makes mutations to genomes. So here, let's say we have we're just making sort of one bit changes to this genome. So there are a couple of possible changes we could make. But now let's do the following. Let's say we try making a change to the genome, and if the result is that it produces a pattern, a kind of model organism that lives longer, or at least as long as it's lived before, then we accept that mutation. Otherwise, we don't accept the mutation. It's as if an organism had that mutation, it either lives and produces lots of offspring or it dies out. And then another mutation will be produced for another organism, and you try that instead. Okay, so the thing that is sort of not obvious that it would work, but it does, is that if you use that kind of setup, that you can start, let's say, from an organism that just dies out after one step, and you can go through a progression of steps with going through all these mutations and keeping only those cases where you don't sort of go backwards. And there can be many actual individual mutations that you have to try to get a new winning mutation, so to speak. But what's happening here is we're getting sort of progressively better solutions to the problem of having rules like the ones I showed and having them produce something that lives a long time. Now, so I think in this particular case, here are, in the end, the sequence of mutations that got made to produce those progressively longer living model organisms. But there are many different ways that one could kind of roll the dice to get kind of longer and longer lived organisms. Here are a couple of other examples. Here's another example. In each case, it sort of seems like the system, one's discovering new ideas for how to live a long time, and then one's building on those ideas to produce something which lives progressively longer. And so this is a case where we're sort of seeing an idealized version of biological evolution in action. And one thing that's really notable about this is the solutions that are being come up with for how to live a long time are really complicated. It's not like there's kind of a direct thing where we're just setting up some particular patterns and so on, and they live a long time. If we kind of go ahead, I think I have an example. Where do I have that? I have an example maybe of sort of all possible ways to live a long time. Yeah, here's one. So this shows kind of long-lived examples of systems like this. They happen to have, this one has 2 colors instead of 3, but you'll see that there are certain cases like this one here that has enough structure that you can imagine kind of explaining, oh, that's why it lives a long time. But there are many cases here, most of the cases here, where it's just like, well, it does its complicated thing and it happens to live a long time and then it dies out. So there's no sort of explainable mechanism to it. And that seems so we have to ask the question, well, what's really going on here? What's happening when we have these very sort of complicated structures that just happen to satisfy certain constraints? How is it that we manage to find these complicated structures that satisfy constraints and so on? If we were imagining kind of the fashioning of this by biological evolution, it would be like, well, there's this particular thing that happened to this organism and it caused it to grow that sort of arm here, and then a different thing happened somewhere else, and we're slowly sort of putting this together. That's not what seems to happen in this idealized model of biological evolution. My guess is that's not what happens in actual biological evolution as well. I think the thing you have to understand is that in the sort of, what's happening here is we're sampling the sort of computational universe of possible programs, and we're using the fact that there's immense richness in that space. And there's enough richness that any given criterion that we're trying to satisfy, there's a good chance we'll find a program that satisfies that criterion. It may do it in a different way, its mechanism will be very complicated, but we'll find something that satisfies that criterion. And that's kind of the key thing. So in terms of things I've worked on recently, this concept of the Roolead, this concept of, let's see if I can, sorry, I'm just still trying to learn how I've got this whole thing set up here, but let's go back to this. So this concept of the Roolead, this kind of entangled limit of all possible computational processes, that's essentially asking about what happens with all possible rules for all possible computational rules. And the thing is that there's immense diversity in what those rules do. And what we're saying is biological evolution is kind of exploring rulal space and finding things in rulal space that satisfy the criteria it wants to satisfy. But the key phenomenon there is there's just a lot of very complicated stuff that happens out there in rulal space. Even with very simple programs, there are just very complicated things that can happen. So sort of a key idea related to that is this idea of computational irreducibility. So let me maybe explain a little bit about that and see if I can do an example here. I probably just make an example. It's probably the easiest thing to do. let's use my favorite cellular automata. Again, simple programs. Let's get this to come up again here. Let's see. There we go. And we just do something in real time here. I could use our very latest technology and use our AI notebook assistant and tell it what to do, but I know what to do myself, so I can just type. Maybe make it, let's put it the right size. Okay, so let's say we have a, that's not what I wanted. We have a particular rule here that says how to build a pattern based on asking if there's a configuration of cells that that goes white, white, black, then you get black, and so on. So let me sorry, just a second. Let's just see what that rule implies if we run it, let's say, starting from one black cell. So we can say this, so we could say this. So I'm just typing Wolfram language code to do this. What we're finding is very simple rule, start off from one black cell, very simple behavior. Okay, that's what you might have expected would happen. That's what kind of our intuition is. Simple rule, simple behavior. Change the rule a bit, we get different behavior, but it's still very simple behavior. Well, we change the rule again, we might get slightly more complicated behavior. Let's try this one here. We'll get this kind of pattern that looks like this. If we continue it longer, we end up getting a very intricate pattern, but it's still very regular and nested and so on. Okay, so experiment that I first did, what was it? Gosh, 42 years ago now, 43 years ago now, is kind of just point a telescope out into the kind of computational universe and see what's out there. And just make a table of all possible behaviors that you get starting with these very simple rules. This is what you get. You see that each one of these pictures corresponds to applying a different rule. Much of the time, what you get is very simple. It might just have stripes. It might just have one thing here. Okay, this is sort of my all-time favorite science discovery, big surprise. Rule 30 in this list of rules does something more complicated. So we run that. We say, okay, here's rule 30. Let's run it for 400 steps. This is the pattern of behavior we get. It's got a certain amount of regularity over on the left, but for many practical purposes, this pattern is completely random. You look at the center column of cells here. I've never been able to find any sort of statistical or cryptographic or anything non-randomness in that column of cells. So, okay, so this is a remarkable thing, that from very simple rules, very complicated behavior, I think that's the essence of where a lot of the complexity we see in nature comes from, including the complexity we see in biology. Now, what people had wondered back in 1859 when Charles Darwin wrote his Origin of Species book, kind of the prevailing sentiment was, well, look at the things we humans make. Things like, a watch or something that has all those cogs in it. That's a complicated looking thing. It took a lot of human effort to make that complicated looking thing. Now look at a biological organism. It's even more complicated. So therefore, we can conclude that there must have been some sort of superhuman force that was able to create that additional complexity. Well, originally that was sort of, there was a lot of natural theology type ideas about what that sort of superhuman force might be. When Darwin came along, he kind of said, well, the superhuman force is natural selection operating over the course of millions of years sort of gradually tweaking the form of this organism to be what we see today. And Darwin kind of imagined that that force of natural selection would lead to the complexity of organisms that we have. It doesn't seem to be true. It's hard to explain why a more complicated organism is sort of a fitter organism, and it isn't even operationally the case. But there's this question of kind of, well, what if you're trying to achieve a particular objective? How do you go about achieving that objective? And the point is that what you're doing is you're sampling a space of possible rules, and out in the space of possible rules, most of what's out there is showing complexity. It's showing computational irreducibility. I should explain what the kind of notion of computational irreducibility is. There's this sort of question of how do you predict what's going to happen in a pattern like this? In some of those other patterns I was showing, like, for example, let's pick this pattern here. This pattern, you can, if somebody says, what's going to be the pattern 10 million steps from now? Well, it's not a terribly difficult piece of math to figure out what the results will be, whether there'll be a black square or a white square 10 million steps from now. Actually, this particular pattern, you can think of it as being the binomial coefficients, Pascal's triangle, mod 2, and you're just sort of computing a binomial coefficient to know whether you get a black square or a white square at any position. So it's that we think of as computationally reducible. Even though it went through 10 million steps to find out what the color of that cell would be, you can just fill in a formula and work out what the color of the cell should be. But the question is, can you always do that? That's kind of been the assumption of mathematical science, has been you can get a formula for things, you can go and jump ahead and figure out what's going to happen. Computational irreducibility is the phenomenon where you can't do that. The simplest way to find out what will happen is just to run it and see what happens. And the key thing, I think, in thinking about biology and biological evolution is most of what happens out in the computational universe of possible programs is computationally irreducible. And so if you're trying to find a thing that satisfies some particular objective, chances are you're going to go through computational irreducibility to get there. Now, it turns out that's a really good thing, because even though it means it's harder to predict what's going to happen, it also means that as you go out trying to sort of get to some particular outcome, you don't get stuck. Let's see if I can pull up a picture here. So this is a picture of kind of what happens in the space of all possible programs, asking, starting from a given program, what happens when you make small changes to that program? And does it lead to, in this case, longer lifetimes, shorter lifetimes for the overall pattern? And what we're seeing is, at each step, we're seeing what happens if you go sort of in different directions from the program that you were initially at. This is kind of directions in program space. And these various lines are showing, well, what's the lifetime, the fitness that you get if you go in that direction? So what this is showing is, for example, someplace like here, we're at that pattern, and we're saying, well, if we make changes to that pattern, where will we lead to shorter lifetimes or longer lifetimes? And what this is showing is, well, there are cases where you get to longer lifetimes, and in the case where we're sort of rolling the dice to figure out which one of these branches we should take, as soon as you pick this branch, you will be at a longer lifetime. You would have been able to get to an even longer lifetime if you'd happened to pick that branch. But in this particular sequence, we randomly picked that branch and we were able to go longer. But the question is, there are many branches, so there's a chance that there's a branch that leads to a better result. But the thing is that even if you pick what's happening with computational irreducibility in the space of possible programs is that you're not finding that you're stuck in a place where you just sort of can't escape because because kind of you ended up in something where it was where there was a very organized structure, but there was no kind of way out. The structure, because of computational irreducibility, the structure of the space of programs is in a sense complicated, unpredictable, and random enough that whatever could happen, if you make various random samples, you'll eventually find a case where it does happen. So then what we're seeing here is that computational irreducibility is what allows you to find these longer lifetime things or higher fitness things. But then what's also going on is the actual solutions that give higher fitness are ones that involve lots of computational irreducibility. So in a sense, what we're saying is the way biology works is it uses the fact that there's all this computational irreducibility. Computational irreducibility sort of is the behavior that you get is rich enough that you can find the thing that achieves fitness, whatever your fitness criterion is, and that's but as you sample things, you're necessarily going through things. You're going through things which have computational irreducibility, have this kind of complex, almost sort of organic-looking characteristics. So let me show you a couple of examples of things like this. So one thing one can do is to say, well, what, choose different fitness criteria. Like, for example, instead of choosing the total length, the total height of the pattern, choose something like its aspect ratio, the ratio of height to width. And you can ask kind of, how do you evolve to different aspect ratios? You can, and you can even ask questions like, if you want to achieve aspect ratio 0.7, what are all the possible paths of evolution selecting at all stages for getting to an aspect ratio that's approximately 0.7? So you can kind of explore, how do you achieve getting to that particular outcome? And once again, what you find is that there's lots of computational irreducibility, both in letting you get to those outcomes by randomly sampling and in the ways those outcomes are achieved. I mean, there's a lot of wonderfully exotic stuff that happens out there. Those are some sort of long lifetime outcomes that you get. That's the set of all possible evolution paths. You can think of this as sort of all the things that biological evolution could have done, all the different paths. This is maybe somewhere here is the piece of the possibilities that corresponds to birds, another piece that corresponds to worms or something. And then there are many branches not taken that just didn't happen to be taken in the history of life on Earth. It's an interesting question, what fraction of the branches really have been explored? And in a few cases that I've looked at, more branches than you might expect, a larger fraction of branches than you might ever expect, have actually been explored by biological evolution. But the point is that if you want to say, well, what are the winning cases here? They're pretty complicated things, and it's not the case that there's again, we can look at different kinds of things that happen. I think here's a picture for that type of organism, so to speak, of different aspect ratios you can achieve. And when you think you know what's going to happen, then this is a feature of the computational universe. Even when you think you know what's going to happen, then some weird creature like this shows up. I was sort of thinking of this as the kind of megafauna, dinosaur-like thing, which, by the way, when you look at it, some aspects of what it does are quite explainable, but many are not. But so that's kind of the idea, is computational irreducibility is what lets biological evolution make progress, not get stuck, but what leads it to have solutions to the problem of satisfying fitness in biology, lets it have solutions, but those solutions typically show computational irreducibility that we read as sort of this organic-like complexity of form. So that's a little bit on that. So let's see. Let me see what else people have been asking about here. Let's see. Okay, a bunch of questions here. From George, what insights can this work on biological evolution shed on the computational materials design process? interesting question. I mean, I think one question is, when you're designing materials, what can you design? You can design molecules, individual molecules that have particular forms. You can design alloys, for example, that are sort of mixtures of molecules. You can perhaps design crystals that have a mixture of more than one type of unit cell, more than one type of building block, or you can go beyond that and you can design metamaterials where you have features in the material that aren't just at the level of individual molecules, but they're rather at the level uh, of kind of whole groups of molecules and so on. So I think there's sort of a question of what forms of materials can you evolve in a theoretical way, and then what properties would they have? So, for example, one thing that will happen is a crystal, for example, is a definite repeating structure, and it has, if you shine X-rays through it, then X-rays will be diffracted at particular angles, Bragg reflection, and they correspond to the periodic spacing of the atoms in the crystal. Well, so if you take, for example, a quasicrystal, something made with a non-periodic tiling, you will get different kinds of diffraction patterns. If you take a material like a glass, for example, that doesn't have regularly organized atoms, but the atoms are rather sort of randomly stuffed in there, then you'll get yet a different kind of behavior. The thing that one could ask, so that's an amorphous material. I mean, something like glass, the atoms there are silicon and so on, are just are put in sort of as a random collection. Here, I maybe can show you some examples of things like this. Let me try doing that. This is actually from a project I did maybe a year or so ago. Let me pull something up here. Let's say we are sort of filling in elements of a crystal where we've got the square grid. We're randomly adding a square at some place that's adjacent to the existing square. We're going to fill in just we're going to sort of fill in a fully filled in pattern like this. But if instead, well, we could have more complicated constraints on how we fill this pattern in, or we could have something where we just have a shape. Let's see, is this an example of that? Maybe this is an example where we are filling in. Is that an example of this? I'm not sure. Let's see. I can definitely find an example. Well, here, we're filling in triangular shapes. We can still fill everything up with triangular shapes. On the other hand, if we have a pentagonal shape, pentagons, you can't make a pentagonal tiling just in the plane. Pentagons don't tessellate the plane. Regular pentagons don't tessellate the plane. Squares do, triangles do, equilateral triangles do, regular hexagons do, but pentagons do not. And so you might be filling in this kind of amorphous solid by filling in pentagons, just adding a pentagon wherever one fits, and you end up with these pretty complicated patterns here. There's a more complicated pentagonal pattern. By the way, if you ask the question, it's kind of fun to ask, if you filled in this pentagonal pattern, what are the holes in the pattern like? And there's a definite inventory of holes in the pattern which you can get to find. And it's so, you know, what you would be building with something like this is an amorphous material. Now, there's a question of, can you make something which is a kind of a something that looks random like this. So for instance, if we were to make let's see if I've got an example here. I might have. This is a Penrose tiling. this is a tiling that when you have those two shapes, the red shape and the purple shape, the blue shape, whatever it looks like, there's no way to make those shapes tile the plane so that it's periodic, so that you're just repeating the same elements over and over again. But you can tile the plane in this nested way. You're progressively building up, this kind of nested pattern, this fractal pattern of tilings. You can still tile the plane in that case. There's sort of a question of whether you can have something where you have particular shapes of tiles, for example, where you can tile the plane, but the only way you can tile the plane is in some random looking way that looks like computational irreducibility. Well, so you can show that in principle that must be possible. And I've spent a while looking for actual cases where you can do that. This, by the way, this is an example. This is the hat tiling. There's a recently found tiling where you get a single tile that when you allow the thing and its flip over, you can tile the plane with that tile and its flip over, but you can't tile the plane periodically. And this is, again, one of these cases where the way you succeed in tiling is using this nested, you build up a bigger and bigger pattern where every piece is copies of previous pieces. Well, so sort of an open question that I've been exploring actually off and on for the last 30 years, whether it is possible, let's see if I can find you a picture of this, whether it's possible to get a tiling which is, yes, I might have a picture here, whether it's possible to have a tiling that has definite sort of tiling constraints where you can tile the plane, but the only way to tile the plane using those constraints is something that is a sort of random looking pattern. So here are two examples of sets of constraints. So this is asking those rules at the bottom there are saying around every square tile, there must be a configuration of black and white that has the form, one of the forms specified in that list. So the one on the left has, what is it, 8 possible forms for the configuration of blacks and whites around that square. The one on the right has more forms, but the pictures show kind of that there are tilings and periodic tilings in these cases that can be made satisfying those constraints. And if you keep going, you can find out sort of what are all the possible constraints that you can have, given that you have all the possible tilings that can be forced, given that you have constraints of this kind. Well, one thing that I found back in the early 90s now is this example here, where with those constraints shown at the bottom, and also the additional sort of global constraint that it can't all be white, then this pattern is the only one that satisfies those tiling constraints. Well, this pattern and shiftings of this pattern. And this pattern is never periodic. If you kind of look at it, it's sort of counting in binary. And it's kind of cute that when it counts below 0, it uses effectively 2's complement arithmetic. But this is an example where one gets when one's forced to have something non-periodic. But let me see if I can get an example up here. But it's still quite regular. The question is, can you force non-periodicity? And well, actually, you can with that rather complicated set of tiles on the left, you can force a pattern that looks like the thing on the right. And then with this really complicated collection of tiles down there, you can force something that looks like that Rule 30 pattern. But a question is, can you find a simple set of tiles that forces a pattern like this? Can you even find a set of tiles so simple that it could be implemented readily with particular molecules and so on? If you could, you would have a repeatable random material, so to speak, which would be pretty interesting. There are all kinds of things you can do for sort of physical security, physical cryptography, and so on. There are probably a bunch of other effects you can make use of if you have a repeatably random, at a molecular scale, material. But, so that's one kind of approach. Another kind of approach is if you have a particular objective, you can ask, can you find a way of constructing a material or a metamaterial that satisfies the particular objective you have? And yes, it's perfectly possible. In fact, I've been surprised at sort of how well, if you say, well, I need something which can be produced using these kinds of rules. For example, you might say, I need something which could be produced by having rules that just add something onto the surface of the crystal whenever some small set of criteria is satisfied. Can you find that small set of criteria such that the crystal, in quotes, that you make has some very complicated form or some form that achieves the particular objectives you want? So I think that's something perfectly realistic to do with this general methodology. Let's see. Let's see. On materials design and computational explorations of design space in general, to what extent can we expect pockets of reducibility to show up and be leveraged? That's an interesting question. I mean, that's a very interesting question to which I don't know the answer, but I really like to know the answer. Let me show you some sort of examples there. So, well, let's look at, there's a good example here. I'll come back to, let me share this again. Come back to something like this. These are a bunch of solutions to a design problem. And as we scan over that whole space, if we're looking at the whole space, we are seeing, well, something like this, though that's bad. Something like this, that's kind of the whole space. And the question is, how many of the things that show up here are kind of explainable? Let's see, if we look at how many of them are kind of computationally reducible. So, if we look at these two patterns here, the first one, it's pretty hard to explain what's going on. It's pretty hard to explain why it lives the number of steps it lives. The one on the right, it's a little easier to explain. Once it's made that kind of blade shape, you're kind of often running, understanding what it's doing. If you try, I think these are different initial conditions for that particular case. Sometimes you get this blade, you can explain what's going on, sometimes you don't. I think, let's see. Oh, for some reason my handy slide generating system doesn't, some of these are just blank. Wow, I don't know what these are. So that's kind of, but yes, I mean, the issue is, how often do you wind up with something explainable? It's a good question. What fraction of the space of what's computationally possible is something that we currently consider explainable? It reminds me of something I studied, if I can pull this up, of something I studied in generative AI. Kind of this is the case where you're looking at a generative AI system and you're looking at the case where you're making a picture of a cat in a party hat and you're gradually modifying the kind of internal representation for the AI of what's going on. And the question is, as you walk around the space, this essentially space of possible images, how often do you come across images which we have kind of human identifications for, and how often are these images just sort of out there in interconcept space? So, I think that's an example of just sort of random images out in the space of possible images. And we see that a few of them we can kind of recognize, oh, this is something we can recognize what it is. That's a region of the space of possibilities. And sometimes we can see things in here where we say, oh, that's something that's human recognizable. sometimes not. So in the case of these images, I know that in terms of things that can be described with individual words, it's about 1 part in 10 to the 600 that can be described that way. So that's a case where how often is it? Okay, I should explain another point. When we talk about computational reducibility, what we mean is we have some method of shortcutting the irreducible computation that was done. We have some way of having our more sophisticated computational system make a shortcut. But it depends what's in that more sophisticated computational system. You know, up to a point, we could just start storing answers. Wouldn't get us very far, but that would be a way of sort of forcing computational reducibility, a tiny piece of it. The thing that we're kind of asking is, have we discovered kind of methods that would allow us to kind of jump ahead in these different kinds of systems? So it sort of depends on what discoveries have we made. So in this space of pictures, we might invent a word for a picture that looks like this. You know, I don't know, purple paw prints, which might get shortened P3s or something, and that might become a word in English. And then every time you say P3, everybody knows what kind of a thing it is. But we don't have that word right now, so we have to kind of describe and sort of wave our hands if we're trying to describe in words what's in that picture. So this question of sort of what's reducible depends on what machinery we have set up for ourselves to do that sort of reduced computation. And so this question about how often are things reducible, really interesting question. So another thing I've tried to do, I wonder if I can show you a picture of this, is to look at cases where we can kind of compare, see if I can pull this up, where we can compare things that have been sort of created by human effort versus things that are sort of just found by searching the computational universe. And let's see if I can do that. Hold on a second. There is a project that I've been long trying to do. Eventually I'll get it done. Let me see whether I can pull this up. And it has to do with, let's see, yeah. Okay. It has to do with this cellular automaton called the Game of Life. And it's an early cellular automaton invented in the late 1960s, a two-dimensional cellular automaton. And here I've got a picture that shows what it looks like in 3 dimensions, where I've got kind of, I don't know if I can, yes, I can rotate this. In 2 dimensions, this is kind of a collection of cells in 2 dimensions. This is a particular configuration of cells that involves these localized structures. And you see the localized structures, that's a glider structure that's moving. Those are oscillators that are in one place, but kind of changing progressively with time. This is kind of a structure that's made by that 2-dimensional cellular automaton. And so the question is, well, if we look for a structure that has a feature, like we say it is a periodic with a period of 11 steps or something, how do we find such structures? And over the last 50-something years, people have looked for lots of such structures. And let's see if I can pull up an example here. Let's see if I can find them. Maybe. Well, let's see. This is, I think this is an example of a fairly elaborate fairly elaborate oscillator structure that is kind of set up to, I think it's gradually periodic with some long period, if I remember correctly. And that's its space-time version. But what I'm looking for is something where we're seeing kind of the whole inventory. All right, I think this is such a picture. although it's kind of in a goofed up setup. But anyway, here's a picture that perhaps shows this. This shows, it's kind of backwards here, but anyway, it's something. This shows years from 1968 to pretty much now, and this shows periods of oscillators. And so this is showing in what year the first oscillator of a certain period was discovered. So, for example, an oscillator of period 11 was discovered in 1977. An oscillator of period 17 was discovered in 1997. An oscillator of period 17 was discovered in 1997. An oscillator of period 19 wasn't discovered until 2023. And so you can look at these actual patterns. I'm not sure I can I pull this up right immediately? Let me see if I can. Okay, a little bit of experiments here. No, that's not it. Let's see whether I can do that. Let's, I think we didn't yet teach our notebook assistant how to access Wolfram Data Repository, although I think that's coming very soon. So I might have to do that myself here. Let's go and do that. Let's see if I can do this. Let me see if I can find something here. Well, all right, what I'm looking at is this entity store of collected game of life configurations. And now, okay, let's have it, this is a good thing, all right. Actually, I've got an example here that might just be able to do this. So this says, well, it's asking for pattern type, oscillator, size. Well, let's just do, let's just forget that. And let's say that we are trying to get, well, let's do sort by hash period. Let's see what I got here. That's the entity value that I'm getting there. And, well, let's just see what this comes out with in this form here. Oh, that's no fun. Let me see. Well, let's just copy the code from here and see what, I don't know why this particular thing is asking for, okay, let's take a look at this. So this is saying, that's an entity class. I don't want to select the size. I just want any size here. Is that not going to work? Aha. So let's just say, that was saying, well, all right, let's try take smallest. Why is it saying 35? So that's the smallest 35. I think we want to say period is take smallest of, let's say, 30. What's happening here? Well, if all else fails, we can just look at the whole collection here. Let me do that. I'm still a bit confused what I have to do here, because I would have expected that this entity class, well, let's say here, I don't know why we have to do this. Let's say size this. Oh, well, that's a bad sign, isn't it? Because that, let's see, we are looking for that. Let's forget this, let's forget that. And let's try this. Well, that's not a good sign, is it? Oh, very basic mistake. I should have asked the notebook assistant. I needed to do a register. I needed to register that entity store if I was expecting to use it in this way. So let me I want to do a very elementary mistake. I forgot to tell it I want to use this. And now if I say period this, I'm pretty sure we will get something. Okay, I don't know why it says that, but dimensions image discovery year. Okay, that's a sparse array. All right, so those are period 2 oscillators. We can probably get, let's get, for each period, so let's say this is period, let's say period 11, for example. What do we get here? Oh boy, what is this doing? Well, let's just ask for the entity value of data set, entity value of image of that. Okay, so that's not an image, but let's say entity, let's look here, properties, 52 properties. So let's say, I think we can say, okay, you know what? I am going to ask the notebook assistant what to do. I'm going to say, let's ask it that. And at the very least, it will hopefully be able to read documentation that I can't be bothered to read here and tell us the answer. I'm not, as I say, it doesn't yet know as much as it should about our data repository. Oh, it's trying to actually do it itself. Never a big fan of this, but anyway. Okay, let's get a result. There we go. Entity type has the following. All right. So let's say, okay, so it does have an image property, but for some reason that's not, let's see, what do we want here? Well, I mean, the terrible thing we could do, I can't imagine why that thing, that sparse array, this is what you get for not having a built-in feature for doing this. Well, okay, let's just try, instead of that, let's try sparse array here. Just ask it for the sparse array. That's very strange. Well, there's a bug here in this data repository entry. But what I could do here, let's just hack around it. Let's say, okay, this is, let's try doing this. And let's just try with the image here. Let's forget the discovery year. And that's full of weird stuff. But I think what we could do, is, if we really want to hack through this, we can say, oh my gosh, we could say here, first of array plot of first of that, and let's say image size arrow tiny, and let's go ahead and map that over that result. And what we should get, there we go. So these are lots of different oscillators in Game of Life. So actually, let me just put meshes on them, and then perhaps what we could do here is we could say image, and we could say period, and here we could then get, well, let's just make that quiet so we don't get all those silly messages. Actually, we also don't want to see the output, so let's just, oh, we got the output there. Okay, so that is the period, and so now we can say, take those, and we could say group by that thing, and then the last element of each one. So that will have all the period 2 oscillators, all the period 3, and so on. Then we'll take first of that, and then we'll take, for each of those, we'll take, so that will give us a list of the first example of oscillators of each progressive size. And then what we'll do is we'll take element first 1, 1 there, and then let's say this, and let's label it with the second element there, which is the period, and let's go ahead and do that for line 32. Okay, let's see what we get here. Okay, here we go. This is cool. All right, so this is now showing us oscillators in the Game of Life that have these particular periods. I'm not sure if they're the minimal size ones, but what we see here, oh, I should have done one more thing here. I should have said to this, I should have said there, I should have said sort by the last element. So that will now sort by the periods. And now I can do this. And now I've got a period 2, a period 3, a period 4, a period 5, et cetera, et cetera, et cetera. So this is showing, this is kind of the engineering, this is the solutions for these particular oscillators of these particular periods. So an interesting question is, which of these were constructed by human effort and which of these were found simply by searching possibilities? That's kind of asking the question, you know, can you tell what was engineered versus what was merely discovered or potentially discovered by some sort of irreducible process of evolution. And I don't know the answer to this. I don't know how to determine that, how to even get heuristics for knowing, well, you know, you could ask here, after 50 years of trying, which of these were found by people doing constructions, which is sort of a reducible process, versus which of these were found by just searching all the possibilities, which is kind of an irreducible process. So that's kind of a sense of this question of sort of, it's almost what's an artifact versus what's a natural thing. You know, what if you look at things on the surface of the earth or something, which features show up as kind of human-made versus which ones are made over the course of time by nature and such like. So anyway, a comment on this. Let's see. I'm looking at lots of questions here. Gosh. All right. well, I can, gosh, so many questions about so many different things. Um, uh, okay, there's a question here, a more sort of computational question that's about if I look at higher order cellular automata. So remember, cellular automaton is something where in one dimension, it's just looking it's just looking, oh gosh, I made that same mistake before. It's just looking at what happens one step back. It's saying, take the pattern of cells at a particular step and look at what happens one step later. So the question that was asked is, have you studied higher order automata which look back 2, 3, 4, or more steps in time? Actually, it just so happens that somebody contacted me recently, a person I've known for many years, about more or less that question. And I sent him something which I characterized as a Christmas gift, which was an idea for a class of systems that would look back more steps. There are definitely places where I found it useful to look back more steps. Let me show you an example. Let's see what I can find here. Oh boy, where is it? Uh, let me see here. Okay, here's an example. This is a cellular automaton that instead of just looking at what happened on the previous step, it looks at the cell on the previous step, its left and right neighbors, and the cell in the middle on the step even before that. And it uses a very simple rule to include the effect of the cell 2 steps back. The rule it's using is just an exclusive OR mod 2 type rule, which says if the thing that should come out should be what you would expect from that triple of cells XORed with the cell 1 step earlier in the history. And so one feature of these particular rules is they are reversible, in the sense that if you know the configuration of cells at a particular step, you can both figure out what the cells on a future step will be, and you can go backwards and figure out what the cells on previous steps will be. So it's a good kind of minimal model for sort of reversible computational processes. And you can go and look at lots of different, let's see, here's some examples of kind of reversible computational processes made with rules like this. Sometimes they're very simple to predict what's going to happen. Sometimes they're not. This idea of things which are at an underlying level reversible, but then when you see something like this one here, even though at an underlying level it's reversible, it turns into this complicated mess that you really have to do sort of irreducible computation to invert. So that's one use of cellular automata that look back more than one step. Let me see if I can find this thing that I just sent this fellow. Let me see where it would be. I'm sorry, just take me a moment to see if I can find it. Hold on. Well, maybe I can do a search here. This is just from a few days ago, but I'm already forgetting. Well, if in doubt, let me just do this. I am going to see if I can find it by doing a raw search. in my email. Oh, yes, I put it in the cloud. Here we go. There it is. Okay, that's why I couldn't find it. All right. So the idea here, let me pull this up. The idea here was to make what I was calling memory cellular automata, where you have the where you're looking at the cell and its two neighbors, and then you're looking at a triple of cells, the cell, the previous step, the step before that. And you do two things in the rule. Let's just pull out this, let's pull out these cases here and look at them in a bit more detail. Let's do this. Okay. Here we go. So this is a memory cellular automaton I just made up a few days ago. And this is, so what I'm doing here is I'm looking at something which has just a single, it needs to know both what the previous state was and two states before that. So this is using, and it needs two rules. So in this case, I'm using rule 30 in both dimensions, so to speak. So let's see what happens. I think I might have a better example here than I made, but if not, I can just do it right now. Let's see. Well, why don't I just do it? Let's, when in doubt, just write the code. Oh, here we go. I've got an example here. So this is doing 500 steps, and I'm going to use rule 30 in both directions, so to speak. Boy, that's super boring. That's okay. Let's try using rule 90 in both directions. Oh, that's more fun. Wow, that's a cool picture. Look at that thing. Wow, really funky. Is that, I like that picture. I wonder if that's is it a perfect nested picture? It probably is. It's a little hard to see because these things are actually, it's really kind of interesting because it's sort of a mixture of something that's nested with something that isn't. I'm going to save this notebook so I make sure that I don't lose this. Let's see. Well, maybe we can try running this a bit longer and see whether it, well, let's run it a bit shorter just to see what that looks like. Let's just run it 100 steps. And that's what it's doing. Okay, so it's a bit sort of dotty, so to speak. I'm going to try living a bit dangerously and run it for 1,000 steps just to see what that looks like. Okay. Well, you know, the fact that it's hard to tell between, yeah, I think this is going to be a nice nested pattern. Its nesting rate is a bit weird. Actually, you know what? I can try just for fun. Let me try 500 steps, and let's try not rule 90, but rule 150, which is another one of these things that gives nested patterns. Now that is weird. That pattern is very similar to the previous pattern, although it's a cool looking pattern. I really like these patterns. Let's try, okay, given that we've done this, let's try some other famous rules. Let's try rule 18. So remember, this is kind of the two-way version of this, where it's going. That's kind of weird. It's both. So what's happening here is it's kind of regular for a while, and then kind of it makes a mess later on. So if we just run it for a little while, it would have looked probably pretty regular. Let's just run it for 100 steps. It probably is looking pretty regular, well, it actually isn't looking that regular even there. Let's try running for all sorts of different rules. So let's try running for just 100 steps. let's just try running a sequence of rules. Let's make a table of the first. Let's go up to rule. Let's just go n up to 30, for example, and let's just see what all these different rules produce. Okay, oops, I should have, silly mistake. I should have labeled these things so we at least know what rule we're looking at. And where did I do that? That's not what I wanted. I wanted this. What's going on there? Where's that? Oh, that's the width. T equals 100. Oh, I want to go into this there. And I'm a little confused here. That's the labeled right there. Okay. All right. So now, rule 5, never the most distinguished rule, is just making a checkerboard pattern. Okay. Rule 22, which is a sort of famous, pretty complicated rule, is doing all kinds of wild things. Let's try a few other famous rules. Let's try and remember this is using the same rule both in history and at a particular step. So I think rule 54 is one that got mentioned. That's okay. What the heck is that doing? Let's try running it a bit longer. That was 100 steps. Let's try running it for 500 steps. Okay. Just when we think we understand what's going to happen, totally weird. Okay, what's happening there is it's got sort of periodic wings, and then the center, it's got that structure that is doing something complicated. I don't know whether it's going to repeat, whether it's nested, what it is. We could probably take here, we could probably say, in this, we could probably say, let's say this is, let's see, this is 500 steps. So let's say take that all, and then let's say, I don't know, let's say 350 to 650. So now that will hopefully give us just the, oh, what did I do wrong? Did I do something stupid here? Array plot. That should be right. That is, well, let's ask the, oh, why did it think that the whole array plot is inside the take? Oh, that's the problem. Okay, there we go. Actually, I could have tightened this up a bit more. 400, 600 here. Okay, so that's just showing that center column, but probably if we just looked at every other step, maybe, I don't know. Let's try that. Okay, it's getting a little bit clearer. Let's maybe look at every fourth step. Well, actually, let's look at every other step in space as well as in time. Okay, that's getting a little clearer. I don't know what it's doing, but it's getting a little clearer what's happening there. We're seeing this region get wider. So I suppose we could try running this longer. Let's try running it for 2,000 steps. Again, living a bit dangerously here. And let's try doing this around 1,000. So we want 1,000 minus 100 is 900. 1,000 plus that is 1,100. Okay, so now we're going to try and home in on what's happening on that. Unfortunately, we have to, oh, did I do something really stupid here? Yes, I did something stupid. This should be 1900 to 2100. And now I probably won't kind of have the camera aim off into the distance here, but I'll probably be able to find something close to what I was looking for. Okay, there we go. So now This is the adventure in the center of Rule 54. And is it becoming periodic? I don't think so. Don't think so, but we can check that. Just for fun, let's go ahead and check that. Let's take this and let's do a thing that's find transient repeat of that. And let's say comma 3. And then let's find the lengths of the things that were found. Oh, what happened? Oh, I need to say with t equals 2000. What happened there? Oh, sorry. With t equals 2000 and n equals 54. Okay, now it'll grind for a while, and I suspect it's not periodic, but we're going to know in a moment. Come on. And I'm wrong. Yet again, the computational animal outsmarted me. It is periodic with period 152. So the center region of this particular pattern is, in fact, periodic. So it's really kind of a surprise because lots of these patterns, when we look back at something like this guy, it's definitely not periodic. It may be nested, but it's definitely not periodic. Anyway, the original prompt here, the original question was, what happens with cellular automata that look back not just one step, but more than one step? And as I say, I just sort of defined this notion of memory cellular automata that sort of use two different rules, a rule that is sort of a rule for the current step, and asking how to involve two previous steps. The chap who contacted me had looked at a particular case, I think, of looking at the majority of the cells in that sort of backward sequence. And I was just thinking about, well, what happens if you generalize? So for example, here, just for fun, we could try doing something where we say, let's take two famous popular rules, and instead of this, let's pick Rule 90 and Rule 150. So we're going Rule 90 in one direction. Oh, wow, look at that cool guy. That's really cool, I think. That's an interesting picture. So that's Rule 90 in the, I think, horizontal direction, Rule 150 in the vertical direction. Let's try that the other way around. Okay, very much the same thing. And let's just try a couple of other famous rules. Let's just try Rule 90 and Rule 30. Okay, oh, well, that makes something that looks very much like ordinary Rule 30, although a bit sort of interpreted and modified. Let's try it the other way around, 90 and 30 the other way around. And it won't, there's no reason to think that looking at well, there we go. So that was basically a Rule 90 kind of setup. Let's try something like, I think Rule 22 and Rule 90 might be kind of fun together. Okay, that just made a complete mess. That's sort of the generic, well, it's got a little bit of structure in here that we can see. It's got a little bit of kind of cool texturing there. And let's try something like Rule 22 and Rule 18. Okay, so that makes something kind of dull. I think that's one of the generic patterns of Rule 22. Looks a bit like that. Let's try, how about Rule 110 with itself, first of all? Ha, practically nothing. How about Rule 110 with Rule 90? Oh, that's weird. That's kind of random looking behavior there. How about Rule 110 with Rule 150? Same kind of thing. I'm almost not, don't feel like saving that one. How about if we do it the other way around, Rule 150 with Rule 110? Boring. How about Rule 90 with Rule 110? Boring. How about Rule 30 with Rule 110? Combine two of my favorites. Oh my gosh. They don't play well together. Let's try it the other way around. This one may be a bit more interesting. Okay, sort of interesting. Let's take a look at that. Oh, it's got some interesting structure there. Um, all right. Well, I think it's time for a day job meeting here, so I think I probably have to go. But these are fun. We'll perhaps post some of this to the cloud. People can play with this themselves. This is kind of a typical sort of adventure of uh, of ruleology, kind of the study of simple rules and what they do. This is a very typical ruleology kind of activity. And what will happen if as one gets sort of a feeling for what's going on, then one can start sort of mapping out the space and understanding kind of more and more details. Now, this one here, for example, is probably an example of one that's sort of right at the edge of what is accessible to kind of mathematical analysis. I mean, this object here, I would predict that, it's ultimately a nested pattern. These kind of, I don't know, they sort of remind me of some kind of, fancy cravat like decoration or something. It's There's probably a way one can analyze how these things at least go together. And for example, this is surely a computationally reducible pattern. But there's sort of a question in a situation like this of kind of what fraction of what's produced ends up being nested, what fraction ends up being sort of completely random looking. And then maybe if one was really lucky, because this is something I'm always curious to look for, are things where there is regularity, there is reducibility, but it's a different kind of reducibility than one's seen before. That's a kind of a thing to look forward to. Anyway, well, thanks for joining me here. This was an experiment in a I could even say a new kind of live stream, so to speak, for me. I hope people have had fun here, and if maybe we'll do some more of these, and maybe I'll ramp up to doing 3 live streams per week. We'll have to see. But I had fun here, so I hope other people did too. Thanks for joining me. See you another time. Bye for now.